I've been thinking about this topic for quite a while, the idea of gravity in the lab, and so I'm really excited to see you all here. It's really great to see that the wheels are turning in a serious way. Today I want to tell you, change my title a little bit. I want to tell you about, in the spirit of meeting in the middle, what's the simplest possible realization from a complexity point of view, a model that theorists would agree has some real serious feature of gravity. So let's say it's going to be a variant of SYK in this case, but the comments could apply more generally. And so what's the simplest possible way to make something like that? And instead of the very interesting talks we heard earlier about realizing SYK in a solid state system, I'll think about actually a digital simulation. So if you had a quantum computer like Sycamore, or maybe version 3 of that in a couple of years, what's the most efficient thing you could do if gates are precious to actually realize this gravitational physics? So what I'll actually do is I'll talk a few inspirational, hopefully, comments at the beginning, more broadly, and then I'll tell you something technical, just a flavor of it towards the end. There will also be a quiz. Okay. So, let me first remind you that this constructing spacetime is possible and interesting. I'll be quick here. We already heard about this, but the basic idea is that if we combine holographic duality, which at least occurs in some funny kinds of systems, as far as we know, with, say, a universal quantum computer or some other kind of programmable or controllable quantum system, we can combine these two things and realize in the lab an experimental simulation of quantum gravity. Now, one thing I want to emphasize is that this is a simulation of some model of quantum gravity. It shows in principle these models that quantum mechanics and gravity can coexist. Of course, we have to go ask in our actual world how it works, and we could get a curveball. That's always interesting. But even if we do, even if it's somehow radically different than what we see here in this sort of holographic duality setting, I think we have to understand this sort of situation very thoroughly, regardless, in order to understand it, what we're seeing in the experiment 100 years from now with graviton colliders is not what we think. Okay. So, and quite apart from that, understanding these connections are quite interesting from the point of view of quantum information, many-body physics, and many other things. So it's really worthwhile to do this. I want to mention that there are some fine print. For example, this simulation pretty much addresses these sort of universes in a bottle here, holographic universes, where what's inside is encoded on what's outside in a very direct way. Of course, theorists are thinking very hard. The whole community is thinking about how to extend this to other kinds of spacetimes, to flat space or de Sitter space. And there are a lot of good ideas. I won't talk anything about it. But I think it's fair to say that it's not nearly so well understood as this ADS-CFT case. Just to give you one extremely biased example of what people are thinking about, I'll tell you one idea very quickly that we had recently. So here's the quiz. Only experimentalists can answer. Based on this picture, what state am I going to talk about? Anyone? The thermofield double state? Okay, but I had one more ingredient here. I've put a line, a red line, and part of it's lightly colored. What that means is I've measured one half of it. So now I only have a state on one side. Okay, and that's actually what's being shown here. If you measured one half and got some state B out of the measurement, then what you get on the other half is this state B, but evolved in imaginary time a little bit. Now, why would you consider something like that? Well, it turns out that one way you could try to get cosmology, for example, is taking ADS-CFT and trying to massage it into a situation where it's sort of unusual and funny kind of setup that maybe you have some interesting dynamics in the state. So, for example, what's happening here is an attempt to realize what's called brain world cosmology. So that's the idea that we live on a brain, say a 3+1 dimensional brain, which lives in some higher dimensional bulk geometry. And for some reason, maybe this brain is moving in ADS, into de Sitter space. The higher dimensional geometries, gravitational modes, some of them are approximately localized to the brain. And so we could try to engineer something like that microscopically in ADS-CFT. This was an idea that we had with a bunch of people at UBC, and then my student Stefano made some more progress on actually demonstrating this localization in a concrete model. So the important takeaway here is just that this is another kind of state that you could make in the lab. You first make the thermal field double, you then measure it. You have one of these sort of beasts here. and then you could do things with it. And so maybe that's another way that you could probe different kind of space-time. But this is just one simple idea, and we need many more. Okay. Now, it's possible, as I said, it's also interesting. Of course, from my point of view, what's interesting is that there are lots of hard questions, like questions related to quantum fluctuations, finite n effects, all kinds of other stuff, which we'd like to know the answer to, but our calculational techniques are just not up to speed yet. You know, maybe they will eventually be, but nevertheless, if you can't calculate, why not just measure? That's been a very successful strategy so far. And so I won't describe these things in any detail, but there are various kinds of concrete questions where maybe we have an expectation for what the physics should look like when you include, say, a quantum correction, but it's very hard to compute. One example would be, we heard a bit about the spreading of chaos earlier. Spreading of chaos in space. If you make a small perturbation locally, that perturbation spreads out. Typically, it spreads out ballistically. But if you look at the length scale over which it goes from being unperturbed to perturbed, that length scale can also grow with time. In a one-dimensional chaotic system, it grows diffusively. And we think that's universal, but actually calculation is very hard in ADS-CFT. We don't know how to do it yet. And so maybe actually we could beat the calculation by just measuring and seeing if it's there. There are lots of other mysteries associated with black holes. For example, just understanding what are called small black holes in ADS, I think, is still a very interesting and confusing subject. Another very important question are what are the time scales for evaporation? That's what this figure here is showing. This is like a small, unpublished, small size exact dilation calculation where you take SYK with some small number of fermions and you couple it to a bath, also with some small number of fermions. And the idea is you start with two states in the system in the SYK, which are distinguishable if you have access to the whole system. That's what these black lines are. This is the guessing probability. You try to tell which state you have based on the best possible measurement. And if you have the whole system, that's the upper line, you can tell perfectly. If you have only, say, one qubit out of all of them, you have only a little bit better than half chance to guess the right one. And that probability would go to 0. Okay, so the information stored in the black hole, then as time evolves, information flows out into the bath. So the black hole information goes down, the bath information goes up, that are these red lines. And now you see at very late time, if you have access to the whole bath, you can again recover the information, whereas in the black hole you can't. But what's really interesting is that at intermediate time, at no point, if you have access only to small numbers of degrees of freedom, can you ever tell. So it never looks locally like any information is being transferred. And yet globally, at the end of the day, you go from being able to perfectly know with a black hole to perfectly know with the bath. And we'd like to understand the timescales for these kinds of processes, the timescale for the distinguishability to flow from the black hole to the bath. That's a very crucial question. And so I want to emphasize this point. I mean, you can always, and it's very tempting to just imagine setting up a black hole system and just letting it run and just let it see what it does, and that's going to be really cool to do. But it's also really crucial to have good questions where we have some expectation, but maybe we don't really know what the possibilities are realized. And the experiment can really give us some quantitative, decisive input on, say, what's going to happen or what nature chooses to do. I'll make one more preliminary comment, which is that it's possible that you could have a radical new technology which emerges from this kind of thinking. I'll give you one completely silly idea that I've been playing with for a long time. The idea is, okay, one thing we care about in quantum information is memories. We like to have a quantum hard drive where we can throw it out in the wet and wild world and the information will stay there. And if we happen to live in 4 plus 1 space-time dimensions, we know this is actually possible using some variant of Kitaev's toric code. Okay, well, we have holography that lets us grow a dimension using entanglement. So maybe we can first build an extra dimension in 3 plus 1 dimensions, and then put a code inside that thing. Right? Actually, you can sort of make this work from the bulk point of view. If you know something about the toric code, you can have like a toric code in the bulk, which is being generated holographically by some one-dimensional boundary. And you put various kinds of boundary conditions on this toric code in some funny pattern. And it turns out you can actually encode a qubit in there. And you could even do the same thing in 4+1 using this fancier kind of toric code to actually encode a qubit in a more robust way. It doesn't really work for various reasons, not the least of which is that we don't even know if there is a boundary theory that has the necessary field content to do this. But it's just a sort of dreamy thought. Like, if we really could engineer the geometry of space-time, what could we do? Maybe we could do something crazy. Okay, so let me come to this main point, which is then what's the minimal complexity that we need to make this kind of emergent geometry? So I'll think about the SYK model. I'll just flash this again. You've heard about this several times today. I'll think also about this sort of Q fermion version of it, where I have Q of these fermions interacting at a time. And the only key point here is that every fermion talks to every other fermion. So every possible combination of interactions is present. Okay, now you can ask, okay, suppose I want to just realize this model in a digital quantum computer. Well, people have thought about that. You can try to just trotterize it. Suppose you want to evolve in time, right? You want to see the black hole form and evaporate. That turns out to be very, very expensive. The best current result, actually by some Google folks down the coast, Babbage, Berry, and Nevin, using this qubitization of Low and Chuang, is that the simulation cost for a system of n fermions scales like n to the 7 halves per unit time. So every time step you want to go, you have this cost. Okay, that's better than that. But actually, people have thought about complexity in the context of ADS-CFT. And from that point of view, this scaling with n here is much higher than expected. From ADS-CFT expectation, we thought that the complexity per unit time should be proportional to the number of degrees of freedom, right? You have a computer, it has 100 bits. Each of those bits is doing something every natural time scale, so the complexity should grow proportional to the number of those bits. But here it's saying actually you have a much more expensive cost to simulate this dynamics. In fact, I'll claim actually, as far as I know, there is no quantum algorithm currently known to our species that simulates these kind of models in a time linear in the number of degrees of freedom. Right? So that's actually a challenge to the algorithm community. I think it's just that if you make the right kind of stipulation, if you put some assumption on the kind of state that you're evolving, there is a more efficient way to do this.
You mean on bosonic qubits, that's what you mean?
Yes. But even if you, I'll talk about this a little bit later, even if you allow fermionic gates, it only removes 1 power of n here. Okay, so what I'll tell you about is, in the little bit of remaining time, is something called a sparse SYK model, where we can get the same physics, the same kind of gravitational physics at low energy, but the simulation cost is vastly reduced. So we change this number from n to the 7 halves to n squared. And there's some parameter k that I'll define in a minute, and it's proportional to this parameter k, but that parameter can be order 1. And in fact, here's where the fermions matter. If it was instead of qubits, you had like fermionic gates, it would only be proportional to n here, which is asymptotically what we want from the complexity point of view. And in fact, this actually works for any q, this scaling, as long as you use this 3-scale time here. And so actually, you can access a whole variety of models that you couldn't do otherwise. Here, the simulation cost would scale with q as n to the q. Okay, and this is work that I've been doing with my postdoc Shenglong, with Lenny, and with Edward over the last, I don't know, year and a half now. It's been a while. Here's the basic idea. It's very simple. Let's just take SYK, where all the things talk to each other, and just start deleting some of those interactions, right? We just delete, we prune, remove them. So we introduce a new variable here, and this variable can be either 0, 1, and it's 1 with some probability p. So 1 minus p is the probability that I delete one of these things. And then this k is defined as the ratio of the number of terms, which is the probability that they have a term times the possible number of terms, divided by the number of fermions. Okay. So for example, if k scales like n cubed, as n goes to infinity, that's the fully connected limit. That's what we know and love as the ordinary SYK. If k is fixed as you take n to infinity, that's the sparse limit. And this limit is quite different. In this limit, every fermion only sees a finite number of other fermions in any given interaction. Now, those fermions then see more fermions and so on. In fact, it looks locally tree-like, but where there are long loops in the interaction graph. Okay. In the computer science or the graph theory community, this is like an expander graph, if you know what that is. Or it's like a tree graph where you take the leaves and glue them together in some interesting way. Okay, and so because if you take k fixed, the number of terms is proportional to the number of fermions, this makes the simulation vastly easier. Okay, so I changed the model actually, and the question then becomes, well, let me just mention, this is a kind of random construction here where I delete them randomly. There's also a more uniform construction where you have a lot of structure in your graph that's very useful. I won't go into the details of it. The important question then becomes, though, in this model, for what values of this parameter k, or for what kind of connectivity, do you still have the interesting physics come out? Still have the gravity physics? Okay, I put these slides in gray so you can know you don't have to pay attention to them. Okay, there's some math. We do the path integral. We can find the saddle points. They're the same saddle points. We can look at the quadratic fluctuations. Okay, we can play the game.
Replica indices?
Yes, we did replica and everything. All of the bells and whistles, right? It turns out that, okay, it's still replica diagonal, if you know what that means, but in any event. This is the key point. The point is you can look at the quadratic fluctuations of this model. That's the active degrees of freedom. And in ordinary SYK, there's one special mode, this sort of time superfluid mode that Juan talked about, the Schwarzian mode. And that mode is soft, and that gives you all this interesting gravity physics. And what we can show in this theory is that even in the sparse limit, even if k is as small as 1 over q, you still have a gap in the quadratic spectrum, so there's only one soft mode, which is the gravity mode, and everybody else is gapped. Okay. So this is strong evidence at the quadratic level that the theory we have still has this single special soft mode, the time superfluid mode, the gravity mode, and that's controlling the low energy physics. Now, one nice thing about this model is that we can do larger scale classical simulation, actually, easier. For example, we can do q equals 8 model, which is very hard to do, has a lot of terms. The normal model with 52 fermions would have about 750 million terms in the Hamiltonian. Okay, that's a lot of terms. We can delete that down to 208 or 416, corresponding to k equals 4 or 8. And that's these two blue and red curves. You see they're almost on top of each other. You can really barely tell them apart. So somehow this k parameter almost doesn't matter, somewhat surprisingly. The physics is totally insensitive to it. And then in the black, I show the result of the large N theory, and they're quite close. Eventually, at low enough temperature, they start to diverge a little bit. But nevertheless, you have a quite significant entropy even in this finite N model at relatively low temperature. Okay. You can also look at the dynamics. The dynamics here, I'm showing the 2-point function. So you're looking at this fermion observable. I plot the log of that 2-point function versus time in units of this natural thermal scale. This is the 2-point function that Juan showed you earlier, was fixed by conformal symmetry. And so there's a predicted slope here, which you just compute from the gravity theory. That slope should be 1 over 8, I guess, or 2 times 1 over 8 at low temperature. So here I'm going to pretty low temperature, some particular choice here. And lo and behold, this thing decays more or less exponentially, and you can just fit the slope, and it's within 10% of the value that you predict. Okay. So as far as we can tell, this model, even for a very, very dilute set of couplings, still gives you the gravitational physics. So let me now return back to this this simulation result. So this was the previous best here for SYK, for full SYK. Now by going to this quantum, this sparse limit, we can get that down to n squared. And so, for example, in this paper, they said, let's think about a first generation fault tolerant computer with 100 logical qubits. You would need, to do n equals 100 here, you'd need 10 million T gates. Okay, some kind of hard to do gate, right? That's a lot of gates. Here, that would reduce the gate per time step by a factor of 1,000, right? So 3 orders of magnitude, you're bringing it closer to life. And in fact, we're thinking now about whether it's possible to even remove this power of n. Here it's using this Jordan-Wigner encoding for fermions, which is a little bit expensive. There are more efficient encodings, probably Kitaev. And it's possible that combined with some trotterization approach, which takes advantage of the sparse structure, you could actually get this down to something of order n log n. So then you'd be saving 10,000 or 100,000 gates per time step. And I think you still couldn't quite call that near term, but it's getting there. Right. And of course, we can also do bigger system size classically because there are fewer terms in the Hamiltonian, so it takes less time. But actually, what's interesting is there may even be novel kinds of classical strategies. So for example, because it has this local tree-like structure, in some cases you can use a tensor network to study these kind of locally tree-like models. So maybe, and we're thinking about this right now, maybe down the road we can do 200 Majoranas classically with a tensor network, at least up to some time scale, right? Maybe we don't even need the experimentalists. Maybe, we'll solve our own problem. So you have a narrow window before the tensor networks solve all the problems. Another way to try to get rid of this extra power of n here is to go to a bosonic model. That's an interesting question. Is there like a spin model which would have this physics? There, in some work with Chris Baldwin that will appear hopefully next week, we show that there's something funny. Actually, for a very broad class of these kind of bosonic models, it turns out that one feature of fermionic SYK is never reproduced at low temperature. You always have some kind of loss of this self-averaging property. That doesn't imply there's no gravitational description, but it's somehow more complicated. So it seems that there's really actually something special about the fermions, which is a little bit magical here. And maybe there's something deep there. I don't know. Okay, so let me wrap up. Quantum gravity lab is possible. That's great. That's why we're here. I hope people in the previous talks have convinced you that, and also tomorrow, that there's actually a lot of interesting questions that you can investigate right now. Not full-blown gravity questions, but things inspired by gravity or related to gravity. Probably we need a fault-tolerant quantum computer or some very finely controlled system that's a little bit still to come. But actually, even just the process of understanding how to implement these things in the lab or on a computer is instructive, and we learn a lot doing it. I told you that, okay, we can do this construction from entanglement and complexity and chaos. These are the ingredients, but they're actually basic algorithmic questions we don't understand still. And one thing we found kind of interesting is that they have this sparse SYK model, which as far as I know is basically currently the least complex, the easiest to implement on a computer model that exhibits this gravitational physics. And this model is interesting for other reasons. It has connections to quantum codes. I already mentioned the idea of new classical simulation approaches. So I think it's part of a general class of like models on sparse graphs that's quite interesting to think about regardless. And I'll close with 2 ads. This is not ADS, this is just an advertisement. We have a winter program in Aspen. My co-organizers, Aaron, Conrad, and Catherine, talking about quantum information and fundamental physics, dark matter, quantum gravity, all kinds of great experimentalists doing amazing things. If you want to apply, you can go to the Aspen website. And then, in the spirit of advertising possible collaborations here as well, I'd just point out that we have this DOE-supported consortium called GeoFlow, with a lot of people in the audience here, which is especially focused on the sort of interface between theory and experiment in the near-term device world. Okay, so we'd love to hear from you and talk about what can be done in this context. All right, thank you very much.